Okay, let's continue. So let's find the solution set for this. So we follow the steps. Solution. So the first one is we start by writing the coefficient matrix and then now the augmented matrix. So the coefficient matrix of this is 1, -7. Then we have 0, we have 6, and then 5. We have 0, 0, 1, -2, and then -3. And then we have -1, 7, -4, 2, and 7. So that is the first step. So that is the augmented matrix. Now, check whether the first entry is 0 or 1. So if it is 0 or any value, then you need to switch. But in this case, we have value there. It's not 0, so we leave it like that. Now we come to the next step. Now we reduce the first column. So reducing the first column, then the second row here is 0. So we deal with the last one here. So in this case, then the new R3 will now be R3 plus what? Plus R1. R3 plus R1. So 1, -7, 0, 6, 5, 0, 0, 1, -2, -3. And then this one plus this is 0. This plus this is 0. -4 plus 0 is -4. Then 2 plus 6 is 8. And then 7 plus 5 is 12. Now, we have the leading entry here. We have another one here. So again, we need to reduce this. So we need to reduce this one to 0. So here we have again our new R3 will now be R3 plus 4 R2 plus 4 R2. R3 plus 4 R2. So what we get is 1, -7, 0, 6, and 5, 0, 0, 1, -2, and -3. And then we have 0, 0. So -4 plus 4 there is 0. 8 plus -2 is what? Is 0. And then 12 plus -12 is 0 there. Now that has been reduced. So what can we see from here? So we have 2 pivot positions there. So the column which has the pivot position is the basic, has the basic variable. So in this case, our basic variables will now be the first column, which will now be x1, and then the one which has another basic, another pivot position is this, and this one is what? X3. Then our free variable will now be the one which has no, so in this case, this up to this point. So this is actually x1, x2, x3, and then x4. So in this case, we have our free variable as x2, this point, and also our x3. for x. So the basic variable is the one that has the type of solution. So that's the basic variable. The free variable is now writing back this to the linear equation, then what we get here is when we write this back to the linear equation, then it is x1 minus 7x2 and then plus 6x4 equals to 5. And then the next one here is now x3 minus 2x4 equals to minus 3, And the last one there is so our solution set. So our solution set will now be x1. So we take the values of x1 to the other side. So we take the values of x1 to the other side. So these are the values to the other side. So we have 5 here. So we bring our x2. So it will be plus 7x2. X3, we don't have it. X4, which is minus 6x4. Minus 6x4. So our x2 is free variable. So x2 is equals to x2. So that is our free variable. And then our x3 will now be, we take the values of x3 to the other side. So x3 will be equals to minus 3. And then we take this one to the other side. So, and then here, it will be plus 2x4. And then x4 is our free variable, which is x4. So to get the values of x1, x2, x3, and x4, then we can put anything for x1, x2, and x4, because x2 and x4 are what? So we can say x1, x2 can be 0, and also x4 can be 0. X2 can be 1, and also x4 can be 1. So the solution is x1, x2, and x4. So in this case, then the solution set is this, so which is x1, x2, x3 for any number, any numbers x2 and x4, for any numbers x2 and x4. So you can.
So when you're writing that last part of the solution set,
Mhm.
and the free variables, are they always gonna like equal each other and write them out? Like
Yes,
x2,
yes, because
x2?
you can put any value for x2. So in this case, if you put x2 here to be 0, then our x2 will be 0. In this case, this is 0, so this is 5 and then 0. If you put x4 to be 0, then this can also be 0. Okay? So you can put it. So our free variable will just be equal to our free variable. So we take these values to our x1 to the other side. Now for any x2 and for any. So you can now put x2 to be 1 and x4 to also be 1. So in this case, we have infinitely many values of x2 and values of x2 and x4. Any question? Okay. Another example, number C. x1 plus 3x2 plus 5x3 equals to 7. 3x1 plus 5x3 x2 plus 7x3 equals to 9. Then 5x1 plus 7x2, 9x3 equals to 1. equals to 1. So the first step, so we write this one in augmented matrix form. So 1, 3, 5, 7, 3, 5, 7, and 9, and then 5, 7, 9, and 1. So we reduce this. So to reduce this one, then in this case, to get the new R2, then it will be R2 minus 3 R1. And then again, to get the new R3, then you get R3 minus 5. So what do you get? So this is 1, 3, 5, and 7. And then the next one is 3 minus 3 is 0. 5 minus 9 is minus 4. 7 minus 15 is minus 8. And then 9 minus 21 is what? Minus 12. And then the last one here is 5 minus 5 is 0. 7 minus 9 is what? It's minus 2. And then 9 minus 25. 9 minus 25 is minus 16. And then finally, 1 minus this is what? 35, right? Get minus 34. Minus 34. Yes.
The second one in row 3 be -8. It's 3 times 5, maybe 15.
This one?
1 over 2.
So same this.
No, the -2 should not be -8.
So this is 5 minus 5 is right?
Yes.
7 minus
15.
15. Oh, this negative base. Okay. So lastly, then we reduce what? -8 here. So it will now be our new R3 will now be R3 minus 2R2. 2R2. So we have 1, 3, 5, and 7, 0, minus 4, minus 8, and minus 12. The last one will be what? 0. Minus 8 plus 8 is 0. Minus 16 plus 16 is 0. Minus 34 plus 24 is minus 10. Minus 10. So in this case, we have the last row here. If you look at the last row, what is happening? So the last row, we can see that the last row is 0x1 plus 0x2 plus 0x3 equals to minus what? Minus 10, right? Equals to minus 10. And if you still remember, what did we say? If we have the value here and all these are zeros, it is what? So we have the contradictory row. So in this case, the last row here, the third row, is the contradictory row. And therefore, this linear system is what? Is inconsistent. It's inconsistent. It's inconsistent. Any question? Now, what can we see from here? So let's look at the summary. So let's look at the summary here. Now, so there are three possibilities when you're looking for the solution set. So the first one is the linear system has no solution if there exists a contradictory row in an echelon form of the associated augmented matrix. So that is what we have seen in the last example there. Number two, we can also see that the linear system has a unique solution if it is consistent and does not have any free variable. That is what we saw in example number 1, example number 8. And then lastly, the linear has infinitely many solutions if it is consistent and has free variables. That is what we saw in example number B. So these are the three possibilities that we can get from the linear system, the solution of the linear system. Any questions? Okay, let's look at another example, example number 7. Determine all possible values for the parameter h and k in the following linear system, so that it has a no solution, b unique solution, and c infinitely many solutions. If we have this system, x1 plus 2x2 equals to h minus 2x1 plus kx2 equals to minus 8 equals to minus 8. So what are the values of x that can give us no solution, unique solution, and infinitely many solutions? So what do you do here? So what is the solution? So we follow the same steps that we did. So first of all, you write this one in augmented matrix form. So we have the coefficients there are 1, 2, and h minus 2, k, and minus 8. And then we do it. And then we now reduce. Then we now reduce. So when we reduce this, then our new R2 will now be R2 plus 2 R1 plus 2 R1. So what do we get? So we get 1, 2, and H. This plus that is 0. K, so we have K plus what? Plus 4. And then we have minus 8 plus 2 H. Minus 8 plus 2H. Now, what will be the value of K and H so that we have no solutions? So the first one, for the linear system to have no solution, then it means this one should be what? 0, right? It should be 0. And this one should not be 0 for us to have no solution. So the last row should be what? Contradictory. So in this case, for this one to have no solution, then K plus 4 should be equal to 0. And therefore, K should be equal to what? Minus. K should be equal to minus 4. Then, last row, the last entry there, then minus 8 plus 2H should not be equal to what? Should not be equal to 0. So in this case, our H, so if we take minus 8 to the other side, then our H should not be equal to 4. Should not be equal to 4. That's it. So this will now be contradictory. So we must have answer. Now, together unique solution. So together unique solution, then we should not have a free variable. So number B, unique solution. Then it means we should, the whole of it should be basic variable. So this is, let's say this is x1 and x2. So x1 and x2 should be, so x1 and x2 should be basic variables. So in this case, for it to be basic variable, then in this case, K plus 4 should not be equal to 0. K plus 4 should not be equal to 0. So therefore, our K should not be equal to minus 4. Should not be equal to minus 4. So K can be any number apart from -4. And finally, our H can be what? Can be any number. H can be any number. H can also be 0. And this value here can be 0. So any number. As long as this one is, as long as K is not equal. So it can be any number, but it should not be equal to -4. Then lastly, number C, to have infinitely many solutions, then the x2 can be basic and can be free. Can be free variable. In this case, for this to have infinitely many solutions, then K plus 4 can be equal to 0. K plus 4 can be equal to 0. And also 2h minus 8 can also be equals to 0. Can also be equals to 0. So k can be equals to 4 minus 4, and h is equals to h equals to 4. Any question after that? Any question? Okay, so if there is no question, then let's come to section 1.3. This one is the vector equations. Now, number one is the vectors. So let's look at the definition 1.1. So before we look at these, then we can denote the sets of all real numbers by the set of real numbers by the R. We always say that if we have some of the elements of, let's say, A, B, C, then we can say A is an element of real number, which means that A is a real number. A is a real number. A is a real number. So A in that case is in R. So A is an element of R. So A, therefore, is a real number. A real number. So let's look at definition 1.1. Definition. An n-dimensional vector with real entries is an n by 1 matrix. So an n-dimensional vector with real entries is an n by 1 matrix, which we can write this as A. And we use that, or if you're able to write A like that. So A is the vector. E is equals to the entries, which are like A1, A2, then AN. A1, A2, AN. So that is a vector A at the point A1, A2. So this is actually an n-dimensional vector with real entries. And this is a 1, n by 1. So we have n rows and 1 column. We can also write this as brackets A1, A2, A3, AN. So we can use the parentheses A1, A2, A3, where A1, A2, all the way to AN are elements of real number. Elements of real number. Elements of real number. Now, the sets are to n. So these are real numbers to n. R to n of all n dimensional vectors with real entries is called the n-dimensional vector space. R to n, which is, so we have n entries there, n of them. Then we call this one the n-dimensional vector space. We say that two vectors, A, which is equals to A1, AN, and B, which is equals to B1, Bn, in Rn are equal, which you can written as A equals to B. A equals to B. If AI equals to BI, where I for I equals to 1 all the way to n for I equals 1 all to n. And we can also say that if entries in a vector are 0, then it is called the 0 vector, which we can write as 0 vector. So that is 0 vector. So those are the terms that we need to know. Now, let's come to 1.2, the operations. The operations. So how can we add, how can we multiply the vectors? So the operation. So if we let A to be equals to A1, A2, and AN, and B, the vector B to be equals to B1 to Bn. And all these be elements of Rn, and C be the scalar, which is an element of real number. And B and C is the scalar. So this one is the this is not a vector. So this is a vector, this is a vector. It's an element of real number. Then number one, if we add the vector, so vector addition, the vector A plus the vector B is equals to adding A1, A2, all the way to AN plus B1, B2, all the way to Bn. And this is the same as A1 plus B1, A2 plus B2, all the way to AN plus Bn. Now, if we multiply the vectors by the scalar, which you call this one scalar multiplication, then if we multiply the vector C by the vector A, C by the vector A, then it is the same as C, and then the vector which is A1, A2, all the way to AN, and this is equals to CA1, CA2, CAN. Any question? Okay, now, number 3, if we negate negative or vector, then the negative of the vector A is the same as -1 of A, which is equals to negative A1, negative A2, all the way to negative AN. Then if we subtract the vectors, so number 4, a vector subtraction. So if we subtract now A, vector A minus vector B, then this is the same as A1, A2, AN, and then minus B1, B2, Bn, which is similar to A1 minus B1, A2 minus B2, AN minus B. Okay, now example number 1. Example number 1. Now let's the vector A to be equals to 2, 3, and 5. The vector B to be equals to -1, 0, and 2. And C to be equals to 10. Then find A plus B, CA, and A minus B. A minus B. So using the same procedure that we did in the operations, so A plus B is equals to solution is equals to the vector A, which is 2, 3, and 5, plus B is -1, 0, and 2, and this is equals to 2 minus 1, 3 plus 0, and then 5 plus 2, which is giving us 1, 3, and 7. 1, 3, and 7. C multiplied by A is the same as 10 multiplied by 2, 3, and 5, which is giving us 20, 30, and 50. Then finally, A minus B is equals to A, which is 2, 3, and 5, minus B, which is 1, 0, and 2, which is giving us 2 plus 1, 3 minus 0, and then 5 minus 2, which is equals to 3, 3, and 3, 3. So what is the geometric interpretation of now vectors? So let's look at the geometric interpretation of each one of them. So look at section 1.3, the geometric interpretation. So if we let the vector A to be equals to A1 and A2, and B to be equals to B1 and B2, and B elements of R, and they have two vectors here. We have two vectors there, R2. And C to be the element of real number, and C is a scalar. C is a scalar. Then how can we interpret? How can we interpret? Now let's start from the first one. If we are adding A and B, if we are adding A and B. So if we add A plus the vector B, then it is the same as A1, A2 plus B1, B2, which is equals to A1 plus B1, A2 plus B2. Then if we multiply by the scalar, so let's say A, C by A, then it is the same as CA1, CA2. Then if we subtract A minus B, then it is similar to A1, A2 minus B1, B2, which is equals to A1 minus B1, A2 minus B2. Now, how can we interpret this? How can we write this in geometric form? Now, the first one, A plus B. So we write the first one, A plus B. Then if we interpret this, so if we put this one as, we say this one is X1, and this one is X2, X1, and X2. So the first vector, so if we say this is, if we put this one as, the first one as A1 and A2, if we want to locate A1, A2, so we can say if we put this point as A1 and A2, so if we say this one is A1, and then this other point is A2, yeah. Then we can also take this as B1 here, so B1, and then this point is B2. So if we add the two vectors, then once we add it, A1 and A2, then we add now A1 plus B1. When we add this A1 plus B1, then it will take us to another point, which is the same as. So A1 and B1 will now be somewhere there. So in this case, this will get that to that point. Then, so this is now our A1 plus B1. And then, so this is actually that way. And then that is that point. So from the point 0 to A1 is here. From the point 0 to B2 is here. So when we add the two of them, so this is taking us to that point, and also this will take us to that point. So in this case, This one is the region A2. That's B2. A2 plus B2. So at the end of it, then that is our point A1 plus B1, A2 plus B2, A2 plus B2. So if we are adding the two vectors, then it will take us to point A. Now, if we multiply by the scalar, now if A, the vector A is multiplied by the scalar. So if we take this as x1 and this one as x2. So our region A1, A2 is, let's say, this point, A1, A2. If this one is A1, A2 there. So if we multiply by the scalar, then it will take us up to that region here, which will now be A plus C. And this one is A. So this one is actually A, and then this one is B, that is, and this one is A plus. This one is also A plus B. So when we multiply that, then it is now taking us to this point, CA1 and then CA2. CA2. Then finally, when we subtract, when we now subtract, so if this is x1 and this is x2, so if we subtract, so if we have our region here, which is A, and this one is A1, and then we have another region here, let's say here, which is B, and this one is B1, and this one is A1, and this one is B2. Then if we subtract, so looking at this, A1, yeah, A1 minus B1, A1 minus B1. So if you look at this, then it means that since A1 is bigger than B1, so in this case, it is the same as B1 minus what? A1. And this region will now take us to, so it will take us to the negative direction here. And this is our B1 minus A1. B1 minus A1. And therefore, this is our region B1 minus A1. So this is B minus A. That is B minus A. So for this region, so we have our B minus A. B minus A. Okay, so this is the vector addition. This is scalar multiplication. And this one is vector subtraction. All right. So when we meet on Monday, then we will look at the properties of the real vector. Okay, make sure you turn in your homework at 2. Okay, I'll see you on Monday.